In this video, I'm going to prove a theorem about division with remainder for integers, as known as division algorithm. Let a and b be integer numbers with b non-zero. Then there exist unique q and r integer numbers such that a equals bq plus r and r is between 0 and absolute value of b minus 1. And in this case, as usual, q is called the quotient and r is called the remainder. Notice here that we have this phrase, there exist unique. So what does it mean? It means that the proof will consist of two parts, existence part and uniqueness part. It's not difficult to prove this theorem using just axioms of integers, but we're going to give a slightly different proof, which is slightly more intuitive, but we will need to use some basic properties of real numbers. Proof. So first we'll prove existence part. So we will prove it with two cases. So when b is greater than 0 and b is less than 0. So case 1, b is greater than 0. So let us say we have a real number x. So given x, which belongs to the set of real numbers R. Let us denote by this integer part of x so sometimes we will call this function a floor function. By definition, so since it's integer part of x is the largest integer, which is less than or equal to x. So for example, if I say floor of 3.7, it gives me 3. Okay, so from definition, let us observe that x is greater than integer part of floor of x and greater than or equal to, and x is strictly less than floor of x plus 1. And let us define q to be floor of a over b, and let us define r to be a minus bq. Clearly q and r are integers, both integers. Okay, why? Because how did we define q to be integer part of a over b, and r equals a minus bq, so product of two integers give us integer, and then when we subtract two integers, we again get an integer. So r is also an integer number. So we did find that there exist q and r, which are integer numbers, and such that a equals bq plus r by our definition, how we defined r. Now we need to check if r satisfies the double inequality. So need to check By the way, let us denote this double inequality by star. So since we are going to use it, since q is floor of a over b by definition, applying star with x being a over b, we get that floor of a over b, which is q, less than or equal to x, which is a over b, and strictly less than q plus 1. And remember, our b is greater than 0, since b is positive number. We can multiply the last inequality by b and get bq is less than or equal to a is less than bq plus b. Now we can subtract bq, subtracting bq, we get 0 less than or equal to a minus bq less than b. Okay, what does it mean? It means 0 is less than or equal to r is less than b, strictly less than b. And since b and r are both integers, r less than b implies, so r less than strictly less than b implies that 0 less than or equal to r is less than or equal to strictly b minus r. Over here, r and b being integers are very important, because if they were just some real numbers, for example, let's say r was 0.5, b was 1, 0.5 is strictly less than 1. It's true, but if I subtract 1 from b, so 1 minus 1 would be 0, and 0.5 wouldn't be strictly less than or equal to 0, right? So that's why, being b and r integers, this implies this. Thus, we proved that r is in between 0 and b minus 1, and also we proved that there exists q and r, which such that a equals bq plus r, and r has this condition. Now let's prove case 2. When b is less than 0. So we're going to prove this case using case 1's result. So since b is less than 0, we have minus b is greater than 0. So since minus b is greater than 0, we can apply case 1, the result of case 1. But to apply the result of case 1, we need to replace a and b by minus a and minus b, applying the result from case 1 and replacing a and b by minus a and minus b respectively. We get that there exists q prime and r prime in Z such that minus a equals minus b multiplied by q prime plus r prime with 0 less than or equal to r prime less than minus b, or which is minus b in this case is positive, that's why it equals to absolute value of minus b and absolute value of b as well. Now multiplying both sides of the last equality, we get both sides by minus 1. We get a equals b multiplied by q prime plus minus r prime. And we cannot just say that we have this because minus r prime is not in the correct range. Notice minus r prime is not in the correct range. So because since 0 is less than or equal to r prime is less than absolute value of b, implies minus absolute value of b is less than negative r prime is less than or equal to 0. But we can fix this problem. If r prime is 0, then no problem. A is b q prime, and in our case q is being q prime and r is being just 0. If r prime is non-zero, then we can set q to be q prime plus 1 and r to be minus r prime minus b. Then bq plus r will be equal to bq prime plus 1 plus minus r prime minus b, and if we distribute and collect like terms, we get actually our a. So, and yeah, we did write a in terms of q in terms of q and r, bq plus r, and now we need to check if this r is in the correct range. So we know that minus absolute value of b is less than minus r prime less than or equal to 0 can be written as just b less than minus r prime less than or equal to 0, because b is less than 0, it means absolute value of b is minus b, and minus absolute value of b would be just b. Okay, and since we also assumed that r prime is non-zero, we have this: b is strictly less than minus r prime, strictly less than 0. Now subtracting b from both sides, we get 0 less than negative r prime negative b less than minus b. Or it is equivalent to saying 0 less than minus r prime minus b was r, and then minus b is a positive number and it equals to absolute value of b. So what did we do when b was less than 0? We found a q and r, which were both integer numbers, and you could write a as bq plus r, and r satisfies this condition. Okay, now let us prove uniqueness part. So in general, to prove uniqueness part, we usually assume that there exist two distinct things, and then we will get a contradiction, and that will give us that those distinct things were not distinct, they were the same. Okay, so assume we have two distinct pairs qr and q prime r prime satisfying the condition of the theorem. Okay, so what does it mean? It means assume there exist q prime, r prime integer numbers such that we have a equals bq plus r and bq prime plus r prime with this 0 less than or equal to r or r prime both satisfy this inequality, and q and r are distinct from q prime and r prime distinct respectively. So we can rewrite bq plus r equals bq prime plus r prime as just subtract bq prime from both sides, subtract r from both sides, combine like terms, and get this. And taking absolute values, I get this: absolute value of b q minus q prime equals absolute value of r prime minus r. So we know that r prime and r both are in this interval, so might be 0 up to absolute value of b. It's not included, and because of that the distance between r prime and r must be less than absolute value of b. So r prime minus r have to be less than absolute value of b. So now, after this observation, we consider two cases. Case 1, when q does not equal to q prime. Let us say we have this. Then absolute value of q minus q prime is greater than 0, and since these are positive numbers, we can use this fact that then they are greater than or equal to 1. That's why now we have this r prime minus r, absolute value of b, q minus q prime, we already have it, and then this has to be greater than or equal to absolute value of b multiplied by 1, because we said that absolute value of q minus q prime is greater than or equal to 1. It means that our r prime minus r is greater than or equal to absolute value of b, which is impossible because our r and r prime was in 0 to absolute value of b, so their distance cannot be greater than or equal to b. This contradicts r prime minus r less than absolute value of b. Okay, so we know that q and q prime cannot be distinct. And case 2, suppose they're equal. If they're equal, then from b, q minus q prime equals r prime minus r. Since they're equal, I know 0 equals this, and it implies r prime equals r. So what does it mean? It means qr and q prime, r prime, are the same. They're equal. So this contradicts the initial hypothesis that they're distinct. So they are unique. We have q and r, which are integers, such that a equals bq plus r, and they are unique. And also that r has the condition that it's between 0 and absolute value of b minus 1.